Start the recording. So how many remember from their algebra days one-to-one functions, function that is an onto function, you know, a function is a one-to-one onto type function. How many remember that kind of terminology from their yeah, Abby remembers it from it's maybe going back to algebra. Well, we're going to discuss similar concepts here with section 1.9. I want you to feel comfortable with what it means for a one-to-one function, a one-to-one linear transformation, what that means, and then the idea of mapping, an onto mapping. Okay, so let me give you a moment to copy this example down. Okay, so this problem, you know, it sounds a little theoretical. How many recall one-to-one and one-to-one onto transformations? It can kind of get a little bit conceptual, a little bit theoretical. How many kind of recall that from their maybe algebra days, or they've seen this? Yeah, and Benjamin brings up the computer science, the 207. Whenever you have these kinds of questions, okay, they come up like, for instance, in multiple choice. It's always helpful to, if you're unsure about the answer, try to create an example to convince yourself if you know it's true or false. Okay, that's really very helpful. I find that very helpful. So we're gonna work this out step by step. So okay, what I'm gonna do for part A here is I'm going to write the transformation as you see here. Okay, I'm going to write the transformation as you see here. I mean, they wrote it in a certain form on the example page, but it's a matrix transformation. Okay, if x1, I mean, you know, x1 is getting mapped to 3x1 plus 1x2. x2 is getting mapped. Well, hold on. I want to be careful here. I'm not saying this the way I'm going to say it. This scratch that comment. Scratch that comment. You're taking a vector x and you're mapping it into the vector x lives in R squared space, two-dimensional space, and you're mapping it to a vector in three-dimensional space. And this is the rule that does that. Okay, this is the vector in three-dimensional space. Now, we want to determine what the matrix A is that's doing this. This is the matrix A. It's called your standard matrix for the linear transformation. But you can't figure out that matrix A until you rewrite the transformation this way here. And then this way. So I'm taking this problem and trying to make it more concrete. And the goal is we want to show if T is a one-to-one linear transformation. Okay, so I get down to here, and what I'm going to do is I'm going to rewrite my matrix product here. I'm going to rewrite it as a linear combination of the column vectors of the matrix A. Okay, I mean, you learned that you can do that, right? A matrix times a vector is a linear combination of the column vectors of the matrix A, the column vectors A1 and A2. So why does this help us? Again, we're trying to see if this transformation is one-to-one. How does this help us? How does this help us writing the transformation? Maybe I'll put this in blue. You know, we're writing the transformation as this linear combination of the column vectors of the matrix A. How does this help us see that if this matrix, if this transformation is one-to-one, this linear transformation? Well, first thing we'll note is that the column vectors of A form a linearly independent set. They form a linearly independent set. Now, that we note that the columns of A, the column vectors of A, do not span R cubed, but they do form a linearly independent set. And so, based on the picture here, based on this picture, what you're doing is you're taking a random vector, okay, a random vector in two-dimensional space, and you're mapping it to a vector y in a two-dimensional subspace of R cubed. So the space in R cubed defined by the transformation is a linear combination of these column vectors A1 and A2. Well, that's going to form this plane. That's a subspace of R cubed. The plane is generated by the span of these column vectors A1 and A2. Column vectors A1 and A2 are linearly independent. So the mapping of the vector x to the vector y is going to be in the span of these column vectors A1 and A2. And because the vector x, the components of the vector x consist of the coefficient, the components are the coefficients of these linearly independent vectors, it follows that every x in R squared will map to a unique vector y in R cubed, because if you change either x1 or x2, if you change either component, you're going to get a different vector you're going to get a different vector y. Okay, so every vector x gets mapped to a unique vector y in R cubed. It has to be that way. And so T is 1-to-1. Transformations 1-to-1. And this is supported by Theorem 12, Part B, on page 78 in your textbook. That theorem says that the transformation is 1-to-1 if and only if the columns of A are linearly independent. But what I wanted to do was give you a geometric feel for 1-to-1. Does it make sense that if you change either x1 or x2, you're going to have a different vector x. But that different vector x then would have to map to a different vector y by virtue of the fact that the column vectors here, A1 and A2, are linearly independent. Does that make reasonable sense? Okay, Benjamin's comfortable. Haley's comfortable. Good. See, I think examples, concrete examples, can make theorems clear. And that's why I always like to look at examples. And then show the theorem, of course. I mean, anytime you change x1 or x2, you're going to produce a different vector y. So changing x1 or x2 means you have a different vector x. That gets mapped to a different vector y. So, you know, a change in the vector x means you're mapping to a new vector y. So 1-to-1 correspondence. Are there any questions on that before we move on? Okay, well then let's now go to the second question. Does the transformation map r squared onto r cubed? Based on the figure, just based on the figure, what do you think the answer is to that question? Benjamin thinks not. And your instincts are right. Your instincts are right, Benjamin. That's right, Haley. Only a subset. Excellent. That's exactly right. So if we go to the solution for part B, if T were to map r squared onto r cubed, this is r cubed here, that's r cubed. If T maps r squared onto r cubed, then that would mean every vector y in r cubed would be the image of some vector x in r squared. So every vector y in three-dimensional space would have to be the image of some vector x in r squared. Okay, well, let's see if that's true. Let's see if that's true. We'll let the vector y be equal to a random vector y1, y with components y1, y2, and y3. We'll let the vector y be any vector. It could be any vector in R3. Okay, any vector in R3. There's no restrictions on y1, y2, and y3. Question is, does the transformation A times X, when we equal Y, does that matrix equation have a solution for every Y in R cubed? So you can see here why matrix equations are important. You know, sometimes vector equations are important. Sometimes matrix equations are important. It just depends on the situation. So okay, well we're gonna see. So of course the matrix equation here yields a augmented matrix system of equations, an augmented matrix. Okay. So what I do here, of course, we're doing a few row operations, and this is the kind of thing I would expect you to show on the exam. You know, this kind of work, right? So what did I do here? It looks like and it's very fresh because I just worked this example out today. I switched out rows 1 and 3. Wait, hold on. No, wait a minute. Hold on, let me erase that. One moment. Well, I did a lot of row switching, didn't I? I switched here. I switched. Okay, hang on. I switched rows 1 and 3. Okay, I switched rows 1 and 3. And then I switch rows 2 and 3 after. This is why I normally like to do just one row operation at a time, because it can be a little difficult to, you know, when you do multiple row operations in one step, it can be a little difficult to understand it. But I mean, let me just see here. I think we're good. Row, one moment. Okay, and then yeah, that's right. That's right. Row swaps. Okay, so now we get down to here. And of course, I'm going to use the 1 as a pivot to get zeros where the 3 and the 5 are. So we're trying to get this augmented matrix in what form? What form are we trying to get the augmented matrix in? Well, Nafani, we could get it in reduced echelon form, but we only need to get it in echelon form. That's right, Haley. We're only going to really need to get it in echelon form. to answer the question we need to answer. So I took, and I appreciate all participation, I took -3 times row 1, and added it to row 2. And put the result in row 2. And then I took -5 times row 1, added the result to row 3. It's a little sloppy, sorry, hold on. And then put the result in row 3. And then here, and then here, I'm going to just simply, I want to get a 0 here. So all I'm going to do, and I guess I'll put the row operation, I'll put it over here to the left, just because I don't have room. All I did was add rows 2 and 3. And put the result in row 3. How many find it helpful having those row operation instructions? How many find that to be helpful? Any who kind of likes having them there? Uh-oh, I thought I might get one positive response. So maybe we can get one. I got to make this recording look good, class. All right, thank you, Eleanor. All right, that sounds good, Benjamin. That sounds good. All right, so look, here, we get the augmented matrix in echelon form, and the key, of course, is the bottom row or equation. So this part here, the y2 minus 5y3 plus -1 times the quantity y1 minus 3y3 reduces to -y1 minus 2y3 plus y2. The system, therefore, is consistent only for points that satisfy this equation, -y1 minus 2y3 plus y2 equals 0. Incidentally, what is this an equation of? What is -y1 minus 2y3 plus y2 equals 0? What is that an equation of? That's right, Nafani. It's an equation of a plane. It's an equation, and that previous plane, the span of those two column vectors, A1 and A2 on the previous page, that's a plane. That subspace is a plane in three-dimensional space, and that's why I noted above the drawing, you'll see here I mentioned, hey, the span of A1 and A2 is this plane here. But that plane excludes many vectors in R3. So T does not map R2 onto R3. the transformation does not map R2 onto R3. And if the reason is because the columns of A, this is actually part A of theorem 12, the columns of the matrix A do not span R3. They don't span R3. They span a subspace, a two-dimensional subspace of R3. So therefore, our transformation is not an on-to mapping. It's a one-to-one mapping, but it's not an on-to mapping. Okay, so how many find this example helpful, helping make these conceptual ideas a little more clear? How many of you are, okay, thank you, Louis. Thank you, Benjamin. Thank you, Samantha. Thank you, Abby and Francesca. Excellent, excellent. Thank you, Olivia. I'm happy to hear that. Happy to hear that. Thank you, Catherine. Okay, okay. So if you're good with this, we're going to be going back into the ebook here. Okay. All right, and are we? May I move forward? Everybody's done copying. All right, let's move forward then. All right. So, one moment here. I'm going to get to section 1.9. Theorem 10. Theorem 10 is the key theorem for section 1.9. But it's kind of abstract now, right? It's kind of abstract. So what I want to do with this theorem is look at some examples, okay? Look at some examples, and then we'll go back to this theorem. So let me go here. How many of you like goldfish? Okay, good. We got some goldfish. Benjamin likes goldfish. Okay. Eleanor does. I had one, you know. It was given to me as a gift, actually, by an ex-girlfriend of mine, and she thought it would be nice that I learn to take care of a pet. And she thought a goldfish would be easy, but they're not easy to take care of. You got to change their tanks and everything, you know. I mean, so, you know, if you get a goldfish, you of course, a pet, you want to take good care of it. So don't think a goldfish is easy to take care of, but I guess it is compared to, like, you know, a dog or a cat or something. But anyway, let's take a look here. So again, what we're doing is we're looking at transformations, and transformations, I think always in terms of animation, because when you have animated cartoons, objects are moving, they're rotating, they're shifting, they're you know, contracting and expanding. Well, there's mathematics that is involved in animation, matrix mathematics. And of course, to perform a certain transformation, You already saw a couple transformations in section 1.8. But you know, if you want an object to do a certain thing, to act in a certain way, certain transformation, you have to find the right standard matrix of the transformation. And they're showing here some different transformations. So, okay, so how are they coming up with these transformations? Well, the first is reflection through the x1 axis. So what they're saying is the standard matrix that would do this is 1, 0, and 0, -1. So look at the fish. Look at the fish. You can see the fish is getting reflected about the x1 axis. So if you were to take all the little pixels that make up that fish, and every pixel has a coordinate, and you were to multiply that pixel by this standard matrix here, the effect would be the fish motion that you're seeing. But how do they come up with this matrix 1, 0, 0, -1? Well, what they're doing is they're saying if we want to reflect about the x1 axis, let's take the unit vectors 1, 0 and the unit vectors 0, 1 and see what would happen. Well, the vector 1, 0 would stay where it is because that's already on the x1 axis. But the vector 0, 1 would get mapped to the 0, -1 vector because the 0, 1 vector reflected about the x1 axis would be 0, -1. And so 1, 0 and 0, -1 form the vectors of your standard matrix for this reflection through the x1 axis. If you were to look at reflection through the x2 axis, let's look at that. Okay, well, okay, so the 1, 0 vector gets mapped to the -1, 0 vector. Right? You're reflecting that vector about the x2 axis. So -1, 1, 0, that unit vector gets mapped to -1, 0. Similarly, well, 0, 1, that vector just stays because it just stays. It doesn't get mapped anywhere at all. Well, it gets mapped to itself. And that's how you form the standard matrix for the reflection about the x2 axis. Okay, so are there any questions? Are there any questions? Please ask if you have questions. We'll certainly, why don't we look at one more transformation here? Why don't we look at one more transformation before? Let's go down to here, reflection about the line x2 equals x1. Okay, so, okay, hold on here. So they have here in the first column of the standard matrix, okay, it's called the standard matrix for your linear transformation. They have the vector 0, 1. Why is that? Why is that? Why is in the matrix to the right, in the third picture here, reflection through the line x2 equals x1, why is that vector 0, 1? Okay, that's right, Benjamin. 1, 0 gets mapped to 0, 1. Okay, when you reflect the vector 1, 0 about that 45-degree angle line, 1, 0 gets mapped to 0, 1. Very good. Well, the second vector is in the matrix is 1, 0. What happened there? Why is the second vector 1, 0? Why would that be? Okay, Haley, that's exactly right. 0, 1 maps to 1, 0. You're reflecting that point on the x2 axis to the point on the x1 axis. Very good. We're going to do an example formally, but are there, the book has a lot more. The book has a lot more examples, almost two pages of examples that you can look at. But are there any questions so far? Let's look at here at contractions and expansions. Okay, Francesca, that's exactly what I want to hear. I want to hear when you're not comfortable. Let's see. Okay, all right. Let me go back. Let me go back to that theorem. That theorem here, theorem 10, and I'm going to just do it this way because I know if I do it the other way, this is the theorem that we're applying. This is the theorem that we're applying. We have to figure out how to construct the matrix A, a matrix A that will do the transformation that we want. And so what we do is we say, well, look, all we really need to do is study how the unit vectors E1 and E2 get transformed. And based off of that, we can construct the matrix A. That's really all we need to do. The knowledge of the transformation of E1 and the transformation of E2, those two unit vectors, is sufficient to determine your transformation. That's what this theorem states. Okay, so I'll tell you what. Let's look at an example. I'll show you formally how to do this. Maybe this will help a little bit. Let me go here to let's look at this example. Okay, we're going to do a fairly complicated one. Okay, let's look at this example here. Let me give you a moment to copy it down. Okay, so here we want to find the standard matrix of the transformation that's going to rotate points -3π/4 radians clockwise, and then reflect points through the horizontal x1 axis. Incidentally, how many degrees is -3π/4? How many degrees is that? Well, how many degrees is pi? Okay, good, Samantha. Good, Eleanor. On -135 degrees. All right. So pi is 180 degrees. So -3 times 180 degrees is 540 degrees. And you divide that by 4, and you'll get -135 degrees. Okay, so let me show you how this works. All right, I have pictures to help you. Pictures to help you. 2 pictures. All right, let me give you a moment to copy down the first picture here, and then we'll talk about it. Okay, so what I do here is I first work with the unit vector E1. Now, first thing we're supposed to do is we rotate the unit vector E1 -135 degrees, and that gets us to this vector here with these coordinates. Okay, -√2/2, -√2/2. And remember, the unit, this is a unit vector. So, you know, if you think about, like, if you think in terms of, you know, your trigonometry, okay, you know, if you were to draw, you know, make a right triangle here, you know, how did I get negative root 2 over 2, negative root 2 over 2. Well, this right triangle, the hypotenuse is 1, because if this is this is a unit vector, so all we're doing is rotating that unit vector. That's all we did here, negative 135 degrees, so that's counterclockwise, or clockwise, I should say, 135 degrees. The length of the vector is 1, so by Pythagorean theorem, and you know your trigonometry, this has to be the point. Negative root 2 over 2, negative root 2 over 2. But then what we're going to do is reflect that point through the horizontal x1 axis. So that's what's done here. And so that point then gets mapped to negative root 2, negative root 2 over 2, positive root 2 over 2. And so this is your final transformation of the E1 vector. This is where it ends up. So when you have two transformations, you do them separately. You do the first transformation, and then you take E1 and do the first transformation, and then you transform that point into you get the second transformation and transform that point, and that gets you transformation of E1. Similarly now, so that this is going to be one of the columns of your standard matrix. To get the other column of your standard matrix, you take the vector E2, okay, and you rotate that 135 degrees clockwise, and you're going to end up at the point root 2 over 2, negative root 2 over 2. And again, if you draw a right triangle, your reference angle is 45 degrees here. And so, and of course, this has length 1, the hypotenuse of this right triangle. And so you get root 2 over 2, negative root 2 over 2 for your transformed point. But then what you have to do is you have to then take that point and reflect it about the x1 axis. And when you do that, you're going to get here. You're going to get to root, in other words, the point root 2 over 2, negative root 2 over 2, if you reflect that about the x1 axis, you're going to get the point root 2 over 2, root 2 over 2. And so that's your transformation of E2 here. And therefore, by theorem 10, the standard matrix for this linear transformation is right here, this 2 by 2. And that's how you find the standard matrix. Francesca, does that make a little bit better sense? Seeing the technique there, does that help you feel a little more comfortable on how to find the standard matrix? Okay, excellent. And there's a reason that we use we work with the unit vectors E1 and E2. I'll show you why, why that let me see here. Oh, just debating. I'm looking at this example 1 in the book. It comes in section 1.9. It comes before theorem 10, which we just used, and I'm debating whether to. I guess it's worth probably worth showing. I mean, it is. I mean, basically, you know how to find the standard transformation now for problems you're going to. You have the technique. But let me see if I can maybe convince you why this always is going to work. May I go to example 1 in the textbook? Is everybody okay? Are there any questions? All right, Ariana's good. It's like it's like if you, well, okay, Francesca's good. Great. All right, let me go to this example in the book here. Let me just one moment here. Let me get the book on here. One moment here. Okay, so we applied this theorem in example 1. They say, hold on here. They say suppose that T is a linear transformation that maps the transformation of E1 into the vector 5, -7, 2, and the vector E2 into -3, 8, 0. So we're mapping vectors in R2 into R3. With no additional information, find a formula for the image of an arbitrary x in R squared. And remember, we're told that this is a linear transformation. Okay, so what they do is they say, well, look, we can write the vector x. Any vector x in R2 can be written as a linear combination of the E1 and E2 vectors. Right? That's true. That's for any vector x in R2. So, since T is a linear transformation, the transformation of a vector x, any vector x in R2, could be written as x1 times the transformation of E1 plus x2 times the transformation of E2. That's by the properties of a linear transformation. Well, that turns out to be then this vector here. And you'll notice that the matrix that forms that vector consists of, I want to be careful here, it consists of the column vectors T of E1 and T of E2. Essentially, since any vector in R2 can be written as a linear combination of E1 and E2, it's sufficient to understand, once you understand how the transformation of E1 and E2 is, that's going to form your your column vectors of your matrix A for your standard matrix. Okay, that's an example that helps you. That helps you see why it's true, why this theorem 10 is true. How many find that example helpful so you can appreciate the theorem? I mean, you know how to apply the theorem, but I want you to feel comfortable with why the theorem works. And all right, it's going to take a little time to get comfortable. I understand that. Well, let me go a little further into the book here. Now you have section 1.8 exercises due on Wednesday, but I'm probably going to give you 10 minutes of class. I'm going to have you work actually on section 1.9 since you're just learning it. I think 1.8 you're going to be fine. But look here. Let's see if now maybe this makes a little more sense to you. Contractions and expansions. So what would a standard matrix be to contract or expand? Well, let's say that you wanted to expand or contract your fish along horizontally. Well, that means that 1, 0, that unit vector becomes K0. And depending on whether K is, between 0 and 1, or whether K is greater than 1, determines if you're expanding or contracting. I mean, this would be programmed into a computer if you were, doing animation. This would be, there's matrix multiplication behind animation. And animation's very good today because computers, I mean, you're doing thousands and thousands of these transformation matrices, these standard matrices of the transformation. Well, you'll see what we mean later on, and then you can do vertical contractions and expansions. And here's the standard matrix. And then you have shear transformations. You have these shear transformations. So like, for instance, if you wanted to do a horizontal shear, if you wanted your sheep to be shifted to the left, well, what happens is the 0, 1 vector gets moved to, I want to say, the K1, the vector with components K1. Okay, so I want to be a little bit careful here. Hold on. Yeah, that's right, but I want to just have this. Do you see that for the shears in table 3? Are there any questions on that one? I mean, for this table 3, if we look at the horizontal shear, looking at the top here. Oh, hold on. One moment. Let me get the book back. One moment, class. One moment. Good. Okay, you see there the horizontal shear? What does 1, 0, that unit vector, get mapped to? When the sheet moves to the left or moves to the right, what is does the 1, 0 vector, does that bottom right hand corner for the sheep change? No, it doesn't change. So 1, 0 gets mapped to itself. That's why in the standard matrix here, the standard matrix, okay, that's why 1, 0 stays 1, 0. But the vector 0, 1, if you look at the picture to the left, the vector 0, 1 gets moved which way? The vector 0, 1, that unit vector, gets moved to the, does it get moved to the left or to the right on the left picture? What's 0, 1 get mapped to? All right, hang on. Whatever K1 is, that's right, Hung. That's right. So I think you just need to look at these a little bit and let me stop the recording here. I'm going to let you work on your section 1.9 a little bit. So let me stop the recording.